Hello and welcome to today's webcast brought to you by Lightwave. Today's event, Fiber to the Antenna, will be presented by Phil Shoemaker of the Light Brigade. And this presentation is both live and interactive, so you can ask questions at any time by entering it into the Ask a Question box in the presentation window. If you're having technical questions, you can type in your issue there, and a member of our webcast support team will work with you to correct the issue. If you're running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. A reminder email message will be sent to all registrants with a link to the archive, and it will also be accessible from the home page at lightwaveonline.com. You can also find it at the Event Resources tab as well. And so, some housekeeping issues we're on. Light Brigade, as you know, is a fiber optic training company. We're out of the Seattle, Washington area, but do courses internationally. We're great to be involved with the FTTA market, and been working with several new projects, and the FTTA is definitely one of these. And I'd like to, at this point, have Phil Shoemaker, our SME for FTTA, take over the presentation. I will talk more at the end with the question and answer dialogue, so I hope you stay with us here, and that should be a very informative meeting. Phil, welcome.
Hey, great. Thanks, Larry. Hi, everybody out there. So the big topic here is obviously fiber to the antenna or fiber to the cell, depending on who you're talking to. And one of the big questions comes up is why? And why now? And here we got just a little bit of a study that was taken from online and how many actual mobile devices are in the U.S. And from there, you can see that over the years, from those of us that remember the brick phones and then the old flip phones, and we've gone from analog to digital to 3G to 4G currently, with the anticipation of 5G. And the current trials that are going on out there. And so we kind of give how many devices, and there's actually more devices per capita in the U.S., right? So, and every one of those taking from that cellular system. So that's really why this is coming up, and fiber provides the means to get all that bandwidth and information to where we need it to go. Now, fiber to the antenna is all-inclusive of all these different technologies. So we all recognize macro cells, the big antennas we see everywhere we go, and they can be mounted on a tower. We got images here of being on transmission lines. They can be on water towers, on buildings. And then we get into things that are somewhat more subtle, the micro cells, which is a more concentrated application. Sometimes you might see microcell and DAS being used interchangeably because they both kind of cover this broad-ranging applications. Small cell, picocell, femtocells are things you might find within residential applications, but they're still all considered cell at that point. And fiber makes all of these go as well as they do at that point. So first of all, why fiber? And in this application, one huge advantage is its noise immunity. Electromagnetic and radio frequency interferences, fiber is completely immune from that, so we can run it next to the power lines, up the tower, next to the power that needs to run to the antennas. We can run composite or hybrid cables. In some markets we call it composite. In the antenna market we call it hybrid, where we have power and fiber within the same cabling at that point. So we have a completely pure signal. And the other huge advantage is high bandwidth. And in fact, on single mode fiber, we still talk in terms of unlimited bandwidth, even though theoretically we think it's up into the high terahertz range. And then very, very low loss. And the low loss factor is going to come in when we start talking about the CRAN and these having basically a head end or a central office running the emulated base network and then having antenna arrays coming from that up to 20 kilometers away. So that low loss allows that to happen, and then again the high bandwidth is going to take us all the way to 5G and beyond. Another large advantage here is its small size and lightweight. So here we got a pretty good image of a bunch of coaxial with one single mode fiber next to it. And so the size itself is huge. When you start talking about how many cables are going up a structure or a tower and the load and the strain it puts on those towers, and you can look at any macro cell site and see these massive bundles of cables going up. Those are traditionally old coaxial cables, so size and weight is a huge huge problem there. Here, one single fiber can take care of massive amounts of what we can do with copper. So the weight and size are great. Security. Fiber is it's not impossible to tap, but if it is tapped or the security of it is breached, we know about it instantly. So there's a great advantage for these high secure systems and all of this information going over this cabling. It can be ran in hazardous areas and also covers a very wide temperature range. The major type of fiber being used, especially in the macro cell market, will be a couple of different types of single mode fiber, and we've seen the majority of it being the G.652D. This will allow for CWDM or coarse wave division multiplexing to happen for future growth. And then up the tower, the G.657 bend and sensitive fiber standards have been used, and usually it's the B3 that is the most common of that G.657 applications. And that's more because of the tight bend radiuses and whatnot we might find at the antenna locations. The fiber running to the tower could be a standard single mode fiber, 652D, or if you're running even longer distances, it might even be a long range 655 non-zero dispersion type of fiber would also be a common one to use here. So the different kinds of fiber and which one would apply to your physical needs. So standard single mode fiber, again, the 652D would be the preferred one for most current installs. This is going to allow for using the full optical range of single mode fiber and then get into the optical multiplexing, with CWDM being the more cost-effective of the options here. So you could run multiple systems, multiple fiber, multiple applications off of one of those fibers in that bundle and assigning different wavelengths to different applications. And then the bend and sensitive fibers, the G.657, and here we got a couple of bend radius images, standard single mode fiber and its tolerances to bending, getting all the way down into the G.67B family, which it's pretty amazing. You can wrap it down to a 7.5 millimeter bend radius and find no losses at 1310. And the impressive part of that is even at 1550 nanometers, which is usually historically very sensitive to micro and macro bend. The 657A had really good tolerance at 1310 nanometers. 1550 nanometers still showed a small amount of loss, but the B3 version right now is definitely the most impressive for this market. And then the fiber itself is pretty good, but you also have to cable it, and there's many different cabling options to get the in antenna and to the antenna applications, either inside or outside plant. Your loose buffered applications are going to be the most common getting to the tower, and then the tight buffered applications will be with inside building structures for a DAS application, or a lot of the riser cables going up the antenna have been seen a tight buffered version of this being more like a distribution or breakout. A distribution will be just the tight buffered coating alone, where the breakout, each fiber, you can see the middle cable there on that image, each individual fiber has its own aramid yarn protection, and that provides for even greater tensile ratings, crush resistance, and overall protection of the cable itself. And then again, why the two different versions? Most outside plant applications, the cable is going to go through lots of thermal changes, expansion, contraction, vibration, crush resistant issues, and we find that especially during the thermal cycling of a cable, the loose tube cable is preferred in that case, as the plastics and the polymers that are used in the jacketing materials expand and contract. The fiber itself is able to stay protected and safe through those applications. You see the three images there on how that fiber lays in those buffer tubes. The PVC typical coatings on the tight buffer does not withstand the expansion contraction as much, So usually this could be found for patch cords, inside cabling applications is the most common way you're going to see those designs. So here's a good image on a couple of different versions of distribution cable. You can see that we have some tight buffered cable, aramid yarn surrounding the whole bundle. Very small cable, very small bend radius, so that applies great through conduits. Up tower applications could be used for this, or even within base stations. This is a really good cabling to be used at that point. And it comes in both indoor and outdoor versions. The patch cords we're going to find at the equipment. There's a lot of good cabling out there, and whether you're using single mode or multi-mode, again, all applications are going to work out. But we color code these is a matter of being able to identify it, because you just can't tell from looking at the fiber itself. And so we see we have yellow for your standard single mode, and this will also apply to the 655 and 652T versions. We'll find a variety of colors. If you get into the G.657 fibers, I've seen them in white or dark blue jacketings. And then you start getting into some of the multi-mode versions. Now, we don't see as much multi-mode now as we once did, maybe 10 years ago when the fiber really started pushing into the towers. We saw a lot of the OM2 and then OM3, which you're seeing the aqua color patch version, or the 50 micron versions there. So there used to be orange, now they moved to aqua. And then for other applications, you can see that we have some other colors there for multimode as well. But most fibers you're going to be seeing in these applications are going to be the single mode 652D and again G.657 bended sensitive fibers. One of the most important things when you start running fiber optics inside of buildings will be that you're following code requirements. And we're listing some of the North American requirements here, NEC, National Electrical Code, and Canadian Electrical Code requirements. And they require plenum and or riser specifications depending on how the cable is going to be installed in the building for flame resistance or retardant flame cable, or just the actual strength of cable to withstand its own weight. So we can see most of those will have an OF to start that off with, optical fiber. Non-conductive being the most common. You can see of our 8 cable markings there, there's OFN. For non-conductive, then P, R, or G for general purpose. If for some reason you needed armoring in that cable for crush resistance or rodent protection or some other type of reasons you'd want a more ruggedized cable, you can get conductive cable, could have an armor layer, or even the hybrid cable, since you have conductors in that cable. If you're running power and fiber in the same cable structure, then it gets the C rating. Now, once you go to conductive, you got to make sure you're following NEC grounding requirements. And there's some very specific qualifications for conductive cable within a building. And we're also listing here a reminder on the NEC, generically known as the 50-foot or 15-meter rule. That's when you start bringing in unrated outside plant cable into a building, and due to the toxicity and flammability of unlisted cable, NEC notes that you have to terminate that within 50 feet of building entrance, and it has to be fire blocked properly, and all the issues that come along with that. So in the industry, and those of you that work in many different fiber optic industries, you'll find kind of a confusing term here, and it comes up between composite and hybrid. And antenna applications are not immune to this. So per the NEC, you'll see that anything with conductors and fiber in the same cable jacket will be termed as composite. A fiber that has multi-mode and single mode within the same cable jacket is known as a hybrid. Now you get into the antenna market, and you'll note that a lot of the standards call out for a cable that has power and fiber in it will be termed as hybrid. So be very cautious on who you're talking to and what you're making reference to on how you'd want to term a composite or hybrid cable at that point. It could all be the same thing at some point. And then again, there's definitely indoor style cables, and we got into the distribution and the breakout cables, and they could also be powered as well. But the most common application we're seeing here with fiber up to the top of the towers or to the cell itself, to the antenna itself, is the hybrid, where because the antennas themselves still have to have power, low voltage power at this, so but fiber and the power can be running in the same cable jacketing, which is a huge advantage again, size, weight, and the actual load it puts on these tower applications. Another great thing in the industry, and this will be a great benefit actually getting fiber to the site, is the use of micro cables and microduct. And we can, in comparison, you'll find that usually a micro cable will be about a quarter of the size of standard cables, and they're actually much larger than 288 count now, depending on actually the count you want. We can see some very large micro cables out there now, but this will actually aid in the installation to the tower site, that it won't necessarily have to have the same construction costs that we once had at this point. So the microduct or micro cable could be installed, and then the cable itself is jetted or blown through. And again, it can come in multi-mode, single-mode applications. Typically going to be a small loose tube cable at this point, getting down to smaller coating sizes to maximize the density of the fibers in that cable. And it could also be multi-mode as well if you needed it to be. Now, one of the things we've seen as far as connectorizing these cables in the outside plant has been, we've seen a lot of use of LCs and SCs have been the primary connector styles that are out there. LCs being usually at the antenna locations, SCs being at the base station site, single mode being the most common here. So we see a couple of images. We see on the left a very common connector we're using out here is an LC loopback connector. Actually, no, I'm sorry, that was the SC one. There's an LC version out there as well that's pretty small. And then we also see the LC version of a hybrid connector. You see low voltage power and a duplex LC in the same connector assembly. So those are going to be very common. And the other thing we're seeing that's very common connector-wise in the antenna market is pre-terminated cable. So you won't have to necessarily worry about terminating these in the field. It's all pre-done from the manufacturer of your choice. And then the main difference on when you want to choose an SC to an LC really comes down to size. They function the same. It holds the same single-mode fiber in those connectors, with the LC being about half the size of an SC. So it really maximizes the density of the workspace. At the base stations themselves, we can do field terminable connectors. So if you're running the cable to the antenna cables, again, will be pre-terminated, but you still have to terminate the cable at the base or at the patch panel at the base. And at this point, field terminating by hand is definitely not a recommendation. So you want to use some sort of pre-terminated splice-on options, and they make fused-on options and mechanical options. Both are good for this application as long as the site is secure and thermally stable at some point. And then there's a wide variety of options out there on how you want to terminate. You can see the Fast Connect and the Unicam options there. They kind of all fall into a no polish family, but they're essentially mechanical splice on the inside. And there's a few different fuse connection options out there that also work very well. The image we're seeing here is actually of a what's called a Fast Connect. There's a pre-done fiber stub inside of that connector, and then you cleave the fiber, you slide it in until it touches the fiber inside the connector, then it's locked in place. There's another option that it comes with a pre-cleaved option, which would be the fuse option. At that point, you drop it into your fusion splicer. Currently, we can also see at the bottom of this slide, we have the options of UPC and APC polishes. The UPC is an ultra-physical contact. It gives us very low reflectance, works great for most moderate digital speed applications. But if you start dealing into high-speed, high-power, or DWDM multiplexing options, you may consider going to an APC, the angled physical contact, which gives you very, very low Fresnel reflections. Your overall optical return loss will drop quite a bit. And the biggest indicator to us out in the field, whether it's a UPC or APC, is the color of the connector. Blue, as we're seeing in this image here for UPC, green signifies the APC polish. And you never want to mix and match these. I've troubleshot some systems in the past that they didn't recognize the color difference or didn't realize it made such a large difference, and they plugged the UPC. One's angled and one's curved. Huge, huge problem. So never mix and match those colors. Now, if you're doing any of the fuse options or pre-terminated options, at this point the fuse connects, we see a pigtail option there in the middle, and we see a pre-terminized connectorized module on the far right. These all require fusion splicing. Not that you can't mechanical splice, but at this point, once you've gone to this route, fusion splicing is your best option. It can be a low-cost, what we call a fixed V-groove alignment splicer, like we're seeing on the left, all the way up to our high-end core alignment or profile alignment system splicers that are out there that fully automate the alignment process. They're all a viable fusion splice option. It just depends on the performance that you have to have for that particular job application. One of the items that we test for on a regular basis will be the use of terminators. And the reason that we use these terminators are essentially a way for us to keep the reflection of the very last connector in our system down. And these terminators create a proper glass-to-glass contact, which would directly affect the optical return loss, or ORL, of what we're testing. One of the items that will be tested, the obvious ones are insertion loss or loss of a connector and loss of a splice. But the ORL of the complete system will affect the performance of that system. And so in this case, for proper reflection reading, we want to use a terminator. This is if we're just testing one fiber at a time, again, for proper glass-to-glass contact. Now, the other thing we're looking for, and this is I would say the primary thing we want to look for in the installation of these fiber systems, is proper cleaning and beyond cleaning inspection. And the proper inspection of a connector can be done by hand. A field technician can look into a handheld scope and verify visually clean or dirty, scratched or perfect. But we also have different inspection criteria. And here's kind of the 4-zone option we have per the IEC and TIA standards. And this will verify that the core is perfect with imperfections of usually no imperfections at all, but up to 25 micron for a multi-mode application. Zone B being the cladding, Zone C being the epoxy, and then the full contact zone being Zone D. And then the software and the criteria that mimic the IEC and TIA standards will then get us pass-fail parameters here. So at this point, we want to be using some sort of digital probe that's hooked up to our handheld devices and or our test equipment that can physically see this and verify pass or fail parameters based on these standards, and not just a pass-fail based on the technician's interpretation of what that technician has to be seeing at that point. So anyways, we like to be using the software to physically see that. And so here we got a technician using his handheld device, and he's got a probe, and he's physically plugging it into a patch panel. And this goes, again, a newer version versus the handheld scopes. There's lots of reasons we like this type of visual equipment. For one, it's completely safe. We're looking at an image on a screen. It verifies software, pass or fail parameters, and portable. And we also have the probe. So here he's physically seeing inside of an adapter. This would allow a technician at the top of a tower. So the climber goes up, and obviously you want to have minimal amount of equipment going up into one of these very dangerous locations. And so at this point, very minimal equipment. You can physically see the connector at the antenna, at the squid or the panel that's at the top of the tower. And at this point, we can verify pass-fail parameters with no guesswork at all. And then at this point, if it needs to be recleaned, we'd reclean it, and then we'd re-inspect it. You just don't want to clean blindly. You always have to visually inspect everything when it's done. And this is probably the biggest issue on why fiber systems fail, is they're not cleaned properly, and then they're not inspected properly once the cleaning is done. Because cleaning it once doesn't always get it the way it's supposed to be done in the first place. And again, here's a great example of what a bad inspection might look like. And here we've got a very simple interface. It's a red X for fail, and it would be a green check for a pass. And so with that parameter, there's no guesswork. And even on some of the newer items we've seen on the market, this information could be sent wirelessly to a cloud type of interface, and somebody at the home office could physically be seeing the results in real time if that was possible. So when you get into this and you start doing the visual inspection, you not only want to have the ability to see a connector patch cord or some interface, but you also have to have the correct adapters to see inside of with the probes, inside of that connector port, inside of the transmitter port, and verify that every part of that optical system is clean. Because you got to remember, every connection has two parts. There's two connectors and an adapter. All of those have to be cleaned in order for this to work the way it's supposed to work. And then we have a wide variety of cleaning products out there, and we could probably spend a whole webinar just on cleaning alone, and I'm sure we've done it at some point. So first of all, you have to identify what the contaminant is, and it can be anywhere from basic skin oils to a very coarse sand type environment. So it depends on where your fiber is at, what your current surroundings are. You might get some guys out in the desert, New Mexico, Arizona markets, and they're dealing a lot with sandy, gritty surfaces. And you might get some other market, you might have other types of airborne contaminants. And if you don't clean these contaminants properly, not only going to have high loss, high reflection, but you can physically damage the fiber in those connectors. And I've seen very recent examples of this exact thing happening, that the connectors were damaged due to improper cleaning and or inspection at that point. There are times, we also show some actual cleaning liquids on the screen too, is that you might have to use a wet clean first. You want to make sure it's an approved fiber cleaner, some sort of non-isopropyl or very high alcohol content cleaner, to get maybe some of those coarse contaminants off first, and then a dry wipe to finish it up. And we show all the options there right between, right next to the actual liquid cleaner there. We have some variety of mechanical stick cleaners, and these will clean out the probes and the adapters versus the traditional stick cleaners. We just had a piece of cloth on a cardboard stick, which got it pretty good, but these are a mechanical versions of those. And then the very right cleaner, that is a must-have in every technician's toolkit, and it's a type of real cleaner. There's a clean cloth in there with a pattern on it that pulls and draws away the contaminants off the ferrule and keeps them trapped so you don't reapply them to the connector interface you're trying to do. And again, this would be your number one defense against a failing fiber system, is cleaning and inspection. Then we also have a wide variety of splicing we can do, and I made mention of these earlier in one of my slides for the pigtail splicing. If you're just doing single-strand splicing, the preferred way to splice is what we'd call a Profile Alignment System Splicer, or PAS. So the 3-axis alignment, it brings it on the Z-axis, which is bringing it into close alignment around the electrodes, and then it aligns it on an up and down and side to side, the X and Y views. And it does it by physically having a real-time image of the profile, the index of refraction profile of the glass itself. A lot of people know these as core alignment splicers, and they are the best and the most popular way to splice a single-strand splice. The one drawback that some people have about a PAS splicer is their price points, and they can be a little bit expensive depending on type and brand and model number, so that would be the top-end splicer. There's also cladding alignment splicers and fixed V-groove splicers that are out there. So if your actual profile splicer was too much, there's other versions that you can research, and there's maybe something that works better for you. So actually getting the fiber of the antenna, and this is an actual cable going to an antenna site. This was probably about half a mile away from the actual antenna site it went to. This was tapped off of the mainline cable, and you can see we have a splice closure and proper cable storage. So this all gets into the installation. You want to make sure whoever is doing your installation or whatever contractor or installer you have is that they know the rules. So it's been racked properly. This one also has a locate wire that's built into it. That box that's on the bottom side of that handle or vault is where the locate or grounding function goes into, so you can physically locate this cable where it goes installed. So at that point, it is very valuable for locating that cable down the road or after the point has been done. And once you have the slack in there, we also have a bullet there as updating your as-built. You want to know where your slack is at, how much slack is at those points, and that's usually done by the contractor, and they'll mark up your as-built or your red lines to make sure that they are everything is documented properly for future growth, application, and restorations, repairs. The splice closure itself, this is the key to us getting actually the fiber's protected. The whole purpose of this splice closure is to protect our very fragile fusion splices. And this one is actually done properly. This is a closure in a vault, and the problem with our vaults and our handholds is they are below grade. And depending on where you put these, they may flood. And so for this particular environment, this was here in the area. We've got a little bit of rain up here, and so that handhold filled up with water. It's a good indicator that that splice is floating, which is a great option there when you open up that handhold. That means it's probably sealed done properly. Everything's clean and pristine on the inside of that. So when we open it up to do any adds, moves, or changes on that fiber plane, it's going to be clean as it's supposed to be. If I had opened up that handhold and that was underwater, this might mean you have a little bit more work to do in your project to actually get that closure cleaned up, get to some splices, and then do the job that you meant to do at that point. We can hold all kinds of things inside of these splice closures. Inline splicing is the most prominent one, but currently we can hold splitters in there. We can do what's called optical add-drop multiplexing. Once you start doing CWDM and DWDM applications, the actual wavelength splitters can be put into those splice trays and go off to different cables to different antenna applications. You can go between different splice trays on the inside. They can do cross connects. There's a variety of applications for these splice closures that are out there. Now on the tower itself, they're still technically a splice closure, but they're going to call them a squid. And because when you kind of hold them vertical, or the way they're mounted on the tower at this location, and the fibers coming out of it, the cables coming out of it, it looks a lot like a squid. So that's just a physical description. And they can hold fiber alone. The image on the left is just a fiber only. You can see a couple of LC adapters inside of this particular housing. And then the image on the right is a closed-up version of that same squid, and one was power and one was fiber. We've also seen these squids that can be multiple purpose, and they can be power on one side, fiber on the other. Again, most of these are all pre-terminated like we're seeing here. This particular image we took at an antenna location where all of the actual antennas and the cabling and the remote radio heads, the squids were all pre-done, pre-mounted, and then they were hoisted to the top of the tower, secured properly, and then all the hookups were done by the climbers at that point. But very minimal work was done on site. It was all pre-made, then trailered into that application. Now, within the splice trays, here's an image at an actual base. Pretty good looking job. So here the loose tube cable came into the splice tray. Behind those SC connectors, we can see where the splice tray is holding the physical splices themselves, and then pigtail spliced, pre-terminated connectors, and then properly routed, properly secured. So we're not inducing any stress on the fibers at that point. And this was all in a locked cabinet at the base of an antenna. So you want to make sure that they're color-coded. The color code follows the proper order for 1 through 12, and again, properly secured and organized. And then from this point, we want to make sure everything's cleaned and inspected and documented, and then it can actually be put into service at that point. Once everything has been inspected and cleaned and installed properly, and we've got the type of fiber we want in the cabling, we have to make sure and test everything and make sure that it applies for the standards that were basically assigned to this application. And so we'll actually test it with the OTDR in many stages. For one, we do what's called cable acceptance with the OTDR, and we test that cable before it's installed. We'll verify length and loss of all those fibers, have it documented, and make sure it's good before it's installed. Then we'll actually do span continuity after it's installed. We can measure splice loss, and we'll identify the signatures of the connectors and the splices and verify those are per standard. Then we can also do reflection testing and optical return loss. Similar in concept, but physically different in the case that for no reflection would be the reflection off of a connector or a mechanical splice. Optical return loss is a combined reflection of the fiber and connectors or anything reflective in that span, all coming back to the transmitter, and we can measure that, again, all with the OTDR. Now, the one thing the OTDR doesn't do for us, it doesn't do accurate end-to-end loss, panel-to-panel testing. So we'll also see that, like, we want to test this with our power meters. To get true end-to-end loss, we'll actually use a light source and a power meter, which is physically a transmitter and a receiver to find true end-to-end loss at that point. And so we can check transmit power, receive power, and a true loss between panels. And here we have a technician physically measuring power at a base station and verifying that the power is what's needed to go to the receiver that was at that antenna location. We also have other ways of simple troubleshooting. The VFL, or Visual Fault Locator, is the most common way to troubleshoot short span applications. Bright red laser, they come in different power levels depending on how bright you want it, but usually, again, going to be eye-safe. 5 milliwatts is what's usually the maximum level we're going to see out there. It'll go up to about 4 kilometers down standard fiber with the class 3 VFL at that point. Short span continuity checks, finding bad pigtails, faulty jumpers, dirty connectors are all great ways to do this. And then again, here we have a technician, visual inspection, we saw that image earlier. And then we also have something we can use on single mode fiber, and this is where we want to actually trace a live or a toned fiber. And a lot of people don't realize you can physically tone a fiber. Off of our single mode light sources, we can modulate that light source, and here we're actually clamping on a patch cord at a panel and finding either an active fiber or a toned fiber for proper identifications. And this is much better than just randomly unplugging a fiber you're not confirming is live or not and bringing down X amount of customers at that antenna location. And then in this market, there's a lot of different types of tests that we can do, and this is getting into not just fiber up the antenna. It used to be fiber to the antenna, then just fiber up the antenna, but now it's actually both combined, and we're getting into a lot of different applications here. CPRI testing, which is the actual protocol and language that these antennas are using. So instead of just testing for Ethernet protocols or other types of telephony type protocols, we're doing CPR testing here. So a lot of technicians are getting into the all-in-one testers, which will combine your OTDR, your power meters, CPRI testing, can all be done at that point. And then we have a kind of a brief introduction to that we get into why we test for that. And if you start getting into long-distance, high-speed applications, we also want to get into chromatic dispersion testing. We can also do bandwidth testers. Bit error rate testers can be done at this point. Once again, your fiber plant starts expanding and you start doing multiplexing, you might look into getting an OSA or an optical spectrum analyzer, are all things that we can do to test these fiber plants to make sure that they're going to work for the application again. And these are all antenna applications that all this can be done for. Going back to just the OTDR testing, one of the challenges we have with OTDRs is that they do have a dead zone. And this is a blind spot that you're going to see after every event out there. Now, the issue we have here is that we not only want to verify the connectors at the base station, but we also want to make sure the connectors at the remote radio head at the top of the tower at the antenna are good too. And so one of the challenges comes into is that we like to use loopback connectors. And we saw a brief image of one of those earlier, but we can literally loop fiber 1 and fiber 2 at the top of the tower together and test that. The problem is if we have a 6 or 7 meter dead zone after the first connector, we can't analyze both connectors at the same time. And so we start using 10 meter loopback jumpers so we can see and analyze reflection and loss of those connectors with the OTDR, as well as verifying that the length and everything is what's been needed as well. If you find you have a problem within the OTDR's dead zone, then we go back to our VFL or Visual Fault Locator, and that will help us identify items that are happening in the short distance after that connector at that point. I know these images are a little bit small here, and I apologize for that, but we're actually showing the image on the left is an incorrect way of testing it with a loopback connector. And so what we see, so we got this very long run into the kind of the literally small reflection there kind of in the middle of the screen, and that's at the base station. And then we loop back the connector at the top of a tower, and then after that large reflection, then there's the down fiber at that point. That high reflectance in the middle physically looks like one event, but there's really 2 connectors happening at the same location there. Where the correct version on the right, I can't zoom in here, but when we see this on the OTDR screen itself, we see 2 distinct Fresnel reflections, with a short distance in between. So this is using a 10-meter loopback patch that we can analyze, again, Fresnel reflection and loss of those connectors to verify that they were installed properly, they're cleaned properly, and that we don't have any surprises once the physical electronics are turned on and the site goes active at that point. This image is showing a unterminated, so the very, very high reflection at the end. So we see a couple of very small reflection images on this OTDR trace with one that goes off the top of the screen, kind of in the middle of that image. And this is an unterminated Fresnel reflection. So this is where we get into the use of terminators and proper polishes and all that. And it doesn't matter how good your polish is. If it's unterminated, it's going to show up as a super high reflection at this point. And then we can also see way out to the right of that image a couple of Fresnel reflections popping up out of what we call the noise floor. This is a ghost image, or a harmonic, if you will. It's a double repeat of the highly reflective events we see on the screen, and it can sometimes throw off a technician in analyzing something properly when ghosting comes up at this point. So again, this is where proper termination and Fresnel reflection readings are very important. It also has a very negative effect on optical return loss at this point. And at this point, it looks like we've come to the end of our slide deck, and we've got time here. We have plenty of time for question and answers, and I know we've found some coming along here, but if anybody has questions out there, please, I'll answer those now since we have some time.
Great.
Here's Larry.
Great, Phil. And there are some questions, so why don't I read those off to you? Let's see. One question is there a limitation to standard single-mode fiber?
There are some limitations, and this is where when we get into what kind of single-mode fiber is going to be right, there are some limitations on whether it's what wavelengths you're using and the distances that you're traveling. The one limitation we have, and it's not necessarily a fiber issue, but it's a latency issue. And what you'll find in a lot of the CRAN applications where we have a remote radio head away from the antenna application, we're limited to about 20 kilometers, and this has to do with the latency of the electronics and the timing of the electronics. But definitely G.657B3 for up the tower or to the antenna locations, and standard single-mode fiber up to the tower is going to be great.
Okay, taking off from that question, there's another one that's somewhat related, and in this case, the question is, what type of single-mode fiber and / cable would you recommend for lab use to perform accurate measurements? Loose tube, tight buffered, bend insensitive.
So at this point, what I'm taking from this is they're trying to maybe emulate an antenna application in a lab. And so I would say you want to use, for sure, the fiber. Now, in a lab situation, you don't necessarily, the cable itself is not going to matter in a lab application, but you definitely want to emulate the difference of the bend insensitive and try to mimic the bend radius restrictions you may have, and then the 652D single-mode fiber going to the base location.
Okay, and this question, I'm going to have to interpret it because I think it's, there's supposed to be a versus here. The question is there any benefit to using multi-mode versus single-mode fiber?
Oh, sure, yeah. The one benefit, if there is a benefit to multi-mode fiber, is it's very bend insensitive, just inherently bend insensitive, even though they do make a bend insensitive multi-mode fiber. So for short-range applications, maybe patching together some servers at a head-end location, multi-mode works very well. And sometimes the cost of the electronics can be a little bit lower, but we found some of the single-mode electronics have come way down in price. So the advantages of multi-mode, which used to be price point, have somewhat been weighed out by the actual benefits of single-mode and their lower electronics at this point. And if you physically price out multi-mode and single-mode fiber, the fiber itself, you'll find that single-mode is going to be your better price point option on the cabling and the fiber itself.
Okay, another question here, because it uses a manufacturer's trade name, I'm going to make it more generic. Normally, Splice-on connectors are used in fiber-to-the-home installations. Is there scenarios for for fiber to the antenna as well?
Oh, absolutely. Yeah, anywhere where a pigtail would currently be used, you can use any of these no-polish or Splice-on connectors, whether it be physically a mechanical or fusion option. Those would both be viable operations at the base. Again, nothing done up the tower recommended at this point, because again, we just don't want to take these sensitive electronics to those heights. So this would all be base locations or head-end locations.
Okay, another question. What do you mean by white light? How large should the optical spectrum be? In this case, they're used to using attenuation specified at 1310 and 1550 nanometers. Do you mean the light source should be an LED with a wide spectral bandwidth?
White light. I don't remember saying the term white light. The how large is the spectrum? You're talking about the typical single mode spectrum, so it's running from about 1260 nanometers up to 1677 nanometers or so. Could be the full single mode spectrum that we're using. So when you see the attenuation specified, usually 1310 or 1550 nanometers. The light source at this point that we're going to be using, again, your typical 1310, 1550 test equipment is going to be a great option for you. If you start getting into CWDM or any type of multiplexing options, then we definitely want to start looking at more of a broader range test equipment.
I'll just add, the only case I could think of using pure white light would be a continuity test, and that's just in an intense white light, just normal light, like a flashlight or so. But the normal testing would take place in the normal wavelengths that we're using.
Absolutely, but definitely limited on range. Where red has being the longest wavelength we can see, it's going to go a little bit further than maybe a white light would.
Yeah. Okay, and because you mentioned WDM, there's a question here. Benefit of CWDM over DWDM. Some current cell tower backhaul networks utilizing CWDM are running out of basically channels.
That's an excellent question. So the benefit of CWDM over DWDM is going to be price, for one. As we know, so you're starting to run out of fibers, you got two options when you want to expand your fiber network. You either add more fiber at the price of construction and adding more cable and fiber to your plant, or you have the option of WDM, or one of the versions of multiplexing. CWDM, if you're using the 652D fiber, the zero or low water peak fibers that are out there, you can get up to 18 available wavelengths down that fiber instead of just using the traditional 1 or 2. DWDM comes at a higher price point, but utilizes the 1550 nanometer C band spectrum, but at a higher price point because of its very narrow spectrum, what's needed for that. Both of them are viable options. One has a better price point than the other.
Great. Another question here is, what is active clad splicing?
This is something that's newer out there. So we're very common with active core alignment, and so we had fixed V-groove and we had active core alignment. Now there's an in-between. So at this point, we have the option of active cladding alignment. So it's an in-between. So the optics are a little bit less critical than the active core alignment, and it physically just looks at the cladding, and it still is an active alignment, but it just happens to be at maybe a more cost-effective option to physically splice the fibers.
Okay, another question on polarization mode dispersion. So what is the impact of a PMD test? I guess a measurement. It says fiber length.
Sure, a PMD. So at this current juncture in antenna market, since 20 kilometers happens to be some of the longest fiber lengths we're seeing at this point, PMD isn't necessarily an issue, but it can. So you start looking at 10 gigabit backhaul, 40 gig, 100 gig, and beyond. Then not only do you want to do chromatic dispersion or CD testing, but you also want to do the PMD testing together. Also with reflection testing, fiber characterization becomes a term. So if in your antenna applications and installing fibers and researching this, the term fiber characterization comes up, you definitely want to start looking at PMD and CD measurements. But at this point, you're looking at doing 10 gigabit and beyond speeds to the antenna.
Okay, another question here. Is there a maximum length of fiber from the base station to the antenna itself?
Yeah, I think I've made mention of this a couple of times. 20 kilometers is the current distance I'm seeing, and again, that's not a fiber limitation, and it's not a loss or power limitation. It's literally a latency limitation on how long it takes the signal to go from the base station to the antenna itself, and it's how the actual protocol, how the CRAN needs to communicate to work properly.
Okay, in this question, part of fiber characterization, because there's a typo here, I believe the question is how to minimize optical return loss.
Keep your reflections down. Usually optical return loss, the fiber itself, even though it does give off some Rayleigh backscatter, it's going to be very minimal in part of that equation. The biggest effect that's going to affect your ORL is Fresnel reflection. So if using the current UPC connectors that are cleaned and verified with a 55 dB or less Fresnel reflection, your ORL should be in line. If not, you may need to go to an APC, angled physical contact end-face profile, which should give you 65 dB or better Fresnel reflections.
Okay, without unplugging a port, how can one determine if there's live traffic on a optical cable?
Sure. So here we're at a patch panel again because you're talking about a port location. There was an image there on one of my slides making reference to a fiber identifier. This is a great single mode tool. It only works for single mode. Multi-mode doesn't have a great option for this yet, but for single mode, this puts a macro bend in the fiber and will tell you no light, traffic or light, or if you've had the ability to put a 2 kilohertz tone down the fiber with a light source, you can also tone out that particular fiber.
Extending that, just one minor point.
Sure.
What about the G.657 B.3?
There are some new fiber identifiers on the market that do work with bend-insensitive fibers. You just want to make sure you research it properly and get the right product on what kind of fiber you're working with at that point.
Okay. Okay. I'm trying again to stay vendor neutral here.
Right.
Okay. Polished. I believe the question is hand polished connectors. It could be machine polished versus Splice-on connectors. Is one better?
Sure. Not that I haven't ran into some technicians that can do a very good hand polish in the field, but the problem with anything you're going to field terminate by, we're talking traditional epoxies, lapping films, figure 8 polish on the plate. At this point, those become highly reflective, and on today's single mode market, that's not acceptable. So again, we highly recommend one of the many types of no polish or fuse-on connectors.
Okay, and staying on the back to testing and troubleshooting, what are the key instruments that would be needed for troubleshooting an FTTA system?
Currently, my common is going to be inspection equipment, cleaning equipment, and sometimes just a simple light source and power meter are our primary things to have, maybe even a visual fault locator. You're going to find the majority, easily 90% of all the problems we've encountered have been due to contaminations, improper cleaning, improper inspection. Okay,
and about the loopback devices themselves, again, does this mean that you're going to have 2 technicians, one at the base and one at the top?
You're still going to have a guy at the top to do this. And so there's still the safety issue that comes into tower climbers and the price of tower climbers. But by having the loopback connectors and maybe even some of these all-in-one equipment that can emulate the CPRI, this is where the CPRI testing comes in, is you have the climber at the top of the tower where he's got his basic loopback and his basic inspection equipment. That's all that technician really needs at this point. They can do full-on analysis of all the electronics, all the fibers from the base before the climber comes down. So it can all be done on one trip, one job, saves time, and is a much safer option.
So the loopback connector is being used so that you get the total combined attenuation and reflectance.
Absolutely. It goes up and then comes back down, so I can see loss, reflectance at the connectors on both my transmit and receive fibers all at once.
Okay. Now one notation going back to the G.657 versus the loopback because of the tight turn.
Right, yeah, so you'll find a wide variety of loopback connectors out there. Some of them are made properly with the bend-insensitive fibers. Some have been made with 652 or 652D fibers, and you might see a higher loss at 1550. So definitely buy a quality loopback connector because it can negatively affect your test results if they've been made wrong.
Okay, there was a reference to Terminator several times. What would be the requirement for someone to buy a Terminator to make the reflection testing?
If you have strict ORL or optical return loss readings from the equipment manufacturer that you need to document, or even for troubleshooting, you'd have to have that last connector properly terminated. Or you can use something called a receive box. It's basically, with the OTDR, you got your launch to see the first connector, and then you have a receive box to see the last connector. So those are two options.
Okay, so here's a question. There's still quite a few, so some of these we're going to have to get back to electronically. If the light from an unterminated connector propagates into free space, shouldn't the reflection at such a connector be zero?
Theoretically, yes. But a zero reflectance is the theoretically worst dB you're going to get. Generally, an unterminated connector where the light goes from glass to air will be in the neighborhood of 14 to 16 dB. And that's almost a perfectly cleaved reflection that we'll see with an OTDR.
Okay, so there are some questions that we're not able to get to. However, Phil will be responding electronically to those that we missed. I thank you for submitting those. It's just a time element that's involved. So I would like to thank today's speaker, Phil Shoemaker, etc. And I'd like to also say that the Light Brigade is presenting FTTA custom courses worldwide. So if you are interested, we'd love to hear from you. And on behalf of the Light Brigade, we'd like to thank Lightwave and the Pinwell Corporation. This presentation will be archived within 24 hours and can be accessed from the Lightwave homepage. And again, a reminder email message for the archive will be sent to all registrants, complete with a direct link to the archive. We want to thank you today and look forward to providing you with future webcasts. So thank you very much for attending.